Imagine forces out there, forces so vast, so powerful, they can actually ripple the very fabric of reality itself.
Mm-hmm.
We're talking about gravitational waves today, and we're going to take a deep dive into these, well, frankly, incredible cosmic phenomena.
Absolutely.
So the big questions are, what are these waves, really? And why are they proving to be so profoundly important for how we understand the universe? Okay, let's try and unpack this a bit. For centuries, we had Newtonian physics. Gravity was just this instantaneous force.
Right, action at a distance.
Exactly. Apples fall, Earth pulls them, seems simple enough. But then Albert Einstein came along and just completely turned that on its head with general relativity.
He really did.
Einstein showed us gravity isn't quite a force like we thought. It's more a result of space-time itself curving.
Precisely. Think of space-time as this huge flexible sheet, maybe like a trampoline.
Okay.
And massive things like stars, planets. They're like bowling balls sitting on it, creating these dips, these curves.
And when those bowling balls move...
That's the key. The dips and curves change, and those changes, those disturbances, travel outwards, like ripples on a pond.
Ah, okay, so those are the gravitational waves.
That's exactly what they are. In essence, they're oscillations, you could say, wobbles of that gravitational field, of space-time itself.
Wobbles in space-time, I like that.
Yeah, they are literally ripples in space-time traveling out at the speed of light.
Wow.
And they're generated whenever massive objects move relative to each other in certain ways. And crucially, they carry energy away as gravitational radiation.
Which sounds a lot like electromagnetic radiation, like light-carrying energy.
It's a very similar concept, yes. It's
Yeah.
fundamental to gravity. But something Newtonian physics just, well, it didn't have room for it.
And that's really our mission for this deep dive, isn't it? We want to explore these fascinating ripples, understand the incredible decades-long struggle scientists faced just trying to find them.
It was a struggle.
Figure out what kind of mind-boggling cosmic events create them, how we finally managed to detect them, and maybe most importantly, what new secrets they're already starting to unlock about the universe.
Yeah.
So consider this your shortcut to getting up to speed on something that is, it's genuinely groundbreaking stuff. Now, here's where it gets really interesting, I think. The biggest hurdle, the reason they were so hard to find for so long, is just their incredibly tiny scale.
Oh, absolutely minuscule.
When a wave passes by, it sort of stretches and squeezes the distance between objects. But how tiny are we talking here? Can you give us a sense of that effect?
It's almost hard to picture. Let's take that very first direct detection.
Yeah.
GW 150914.
Okay, the big one.
That wave had traveled for over 1 billion light years, right?
Right.
By the time it reached Earth, it changed the length of one of LEGO's arms, and those arms are 4 kilometers long.
Uh-huh.
Changed the length by just 1/1000th of the width of a single proton.
Wait, 1,000th of a proton width over 4 kilometers?
Exactly. I mean, to put that in perspective,
Yeah.
proportionally, it's like changing the distance to the nearest star, Proxima Centauri,
Yeah.
by the width of one human hair.
Wow. Okay. That's why it took so long.
That's the challenge.
Yeah.
The strain, which is what we call that fractional change in length, is typically around 10 to the minus 21 when these waves get to us. Just incredibly faint.
Makes perfect sense now. And what's fascinating, too, is the history, right? This wasn't just an idea Einstein plucked out of thin air. There were hints beforehand.
That's right. People were thinking along similar lines, drawing analogies with electromagnetism. Oliver Heaviside back in 1893, Henri Poincaré around 1905. They had some early theoretical ideas.
Interesting.
But yeah, it was really Einstein in 1916, working through general relativity, who formally showed that these waves should exist as ripples in space-time.
But even he wasn't totally convinced at first.
Not entirely, no. It's quite a story. He actually doubted their physical reality for a while. In 1936, he even submitted a paper arguing they couldn't exist.
Really?
Yep. But then, after the peer reviewer pointed out an error, he rewrote it, thankfully, concluding the opposite.
Huh. Okay, peer review saves the day.
It certainly did there. It was such a confusing time conceptually that Arthur Eddington even joked about certain wave solutions just propagating at the speed of thought because they seemed like mathematical artifacts.
So it sounds like a real conceptual muddle for a while there. Was there a moment or an argument that really settled whether these waves actually carried energy, whether they were physically real?
There was. Richard Feynman came up with this brilliant thought experiment in 1957. It's often called the sticky bead argument.
Okay, sticky beads.
Yeah, imagine a rod with some beads threaded onto it, able to slide, but with a bit of friction, sticky beads. As a gravitational wave passes, it would try to move the beads along the rod. Because of the friction, this movement would generate a tiny amount of heat.
Ah, so heat means energy transfer.
Exactly. If you can generate heat, the wave must be carrying energy and doing physical work. It was a simple, elegant way to show these waves weren't just some mathematical trick. They were a real physical phenomenon.
And that realization must have really set the stage for the immense challenge of actually trying to build something to detect them.
It did. And people started trying. Joseph Weber in the 1960s was a real pioneer. He built these huge metal cylinders, Weber bars, designed to resonate, to sort of ring when a gravitational wave passed through.
Did they work?
Well, he claimed detections in 1969, quite regularly, actually, but
Oh.
unfortunately, those claims couldn't be replicated. They were later shown to be spurious.
Ah, okay.
But his efforts, even though ultimately unsuccessful in detecting waves, were crucial. They really highlighted just how incredibly difficult this was going to be and spurred on the ingenuity needed for the next generation of detectors.
So decades passed between those early attempts and the first actual direct detection. But there was a really important piece of indirect evidence that came along in the meantime, wasn't there?
Oh, absolutely vital. The Hulse-Taylor binary pulsar.
Right. Discovered in 1974, and it eventually won the Nobel Prize in 93.
That's the one. Russell Hulse and Joseph Taylor found this pair of neutron stars orbiting each other. And by timing the pulses coming from the pulsar very, very precisely over years,
They noticed something changing.
they noticed the orbital period was getting shorter. They were spiraling inwards, closer and closer together, by just the tiniest amount each year.
And this connects to gravitational waves, how?
Well, if you connect this to the bigger picture, general relativity predicts that such a system must lose energy by radiating gravitational waves.
Okay.
And the rate at which Hulse and Taylor saw the orbit decaying, it matched Einstein's predictions for energy loss via gravitational waves perfectly.
Wow. So even though they couldn't see the waves.
Exactly. They saw the effect the waves must be having. It was incredibly strong proof that gravitational waves were real and behaved just as Einstein predicted. This gave huge motivation to keep building the incredibly sensitive detectors needed for a direct detection. It showed they had to be out there.
That's amazing. And just to give people a sense of how weak this effect usually is, think about our own Earth-Sun system. It's losing energy through gravitational waves too, right?
It is, yes, but vanishingly slowly.
Yeah, something like only 200 watts, which sounds like, well, not much for a whole solar system.
It's tiny. At that rate, it would take, what is it, something like 3 times 10 to the 13 times the current age of the universe for the Earth to actually spiral into the sun just from radiating gravitational waves.
Okay, so negligible for us.
Yeah.
But for those neutron stars whipping around each other.
Much, much faster.
Yeah.
Much more significant energy loss. It really put the Hulse-Taylor result into perspective.
Okay, so that brings us to the big moment, the breakthrough. September 2015, the LIGO detectors in the U.S., they finally catch one.
That's right. Livingston, Louisiana, and Hanford, Washington. Both detectors registered a signal almost simultaneously.
So what exactly did they hear or detect that day? What was GW15091 FAIR?
It was the signal from 2 black holes merging. And these weren't small black holes. One was about 29 times the mass of our sun, the other about 36 times.
Wow, those are hefty.
Very. And they were about 1.3 billion light years away. In the final fraction of a second before they merged into one larger black hole,
Yeah.
the amount of power they radiated as gravitational waves was just staggering. More than 50 times the power output of all the stars in the entire observable universe combined.
50 times. All the stars. That's insane power.
It is.
Yeah.
The energy equivalent of about 3 entire solar masses was converted directly into gravitational waves in that tiny moment.
Incredible.
And what's profoundly interesting here, beyond just confirming Einstein again, was the mass of those black holes. They were heavier than astronomers had generally thought possible for black holes formed from stars in binary systems.
So it immediately made us rethink things.
Exactly. It forced us to reconsider how these massive stellar black holes form and how often they merge. And because the signal arrived to the 2 detectors with a tiny time difference, just 7 milliseconds,
Ah, that let them pinpoint the direction.
it allowed them to roughly localize the source to a large patch of the southern celestial hemisphere. A monumental detection, really. And deservedly led to the 2017 Nobel Prize for Rainer Weiss, Kip Thorne, and Barry Barish, the key figures behind LIGO.
Just incredible. So this first direct detection, it wasn't just a confirmation, it really changed the game, didn't it? What's the biggest shift that gravitational wave astronomy has brought?
I'd say it's opened an entirely new window onto the universe, a new sense almost.
How so?
Its unique advantage is profound. Unlike light, radio waves, X-rays, all forms of electromagnetic radiation, gravitational waves basically aren't affected by stuff in between.
They just pass right through dust and gas.
Pretty much.
Uh,
They travel unimpeded across the cosmos, which means they can carry information about events and objects that are completely hidden from our telescopes. Things we've never directly observed before.
like what kind of things?
Well, black hole mergers, involving uncharged black holes, for instance. They don't emit light, or maybe even signals from the very, very early universe.
Before light could even travel freely.
Exactly. A period when the universe was opaque to electromagnetic radiation. Gravitational waves could give us a direct probe into that era. We can now listen to parts of the universe we could never see.
Wow. Okay. And beyond that first huge detection, there have been other major milestones pretty quickly, right? Like the first neutron star merger?
Yes, that was another landmark moment, August 2017, GW170817.
What was so special about that one?
What made it incredibly significant was that it wasn't just detected in gravitational waves. It had an electromagnetic counterpart.
Ah, so we saw it with telescopes too.
We did. First, a short gamma-ray burst arrived just seconds after the gravitational wave signal. Then telescopes quickly found a new point of light, a kilonova, in a galaxy called NGC 4993.
So we saw the same event in two completely different ways.
Exactly. Gravitational waves and light. It was the birth of true multi-messenger astronomy. And having the Virgo detector in Italy online alongside LIGO by then was crucial.
Why was Virgo important?
Adding a third detector dramatically improved the ability to pinpoint the source on the sky. It narrowed down the location by about a factor of 10 compared to what LIGO alone could do. That's what allowed telescopes to find the counterpart so quickly.
That makes sense. The more ears listening, the better you can locate the sound.
Precisely.
And the discoveries just keep rolling in, don't they? I remember hearing about LIGO and Virgo finding the first neutron star black hole binaries in 2021.
That's right. Systems we'd theorized about but had never actually observed before by any conventional means. So yeah, the field is moving incredibly fast.
Which really begs the question, what other kinds of cosmic events are generating these powerful waves? Broadly speaking, what does it take to make space-time ripple like this?
Well, in general, you need large, coherent motions of really immense masses, especially in situations where gravity is extremely strong, where good old Newtonian gravity doesn't quite cut it anymore.
Okay.
But there's a crucial point. Not just any motion will do. Purely spherically symmetric systems don't radiate gravitational waves, meaning like a perfectly spherical star just collapsing inwards equally from all sides. No waves. Or an isolated non-spinning object just moving at a constant speed. No waves either.
So you need asymmetry, something uneven.
Exactly. You need a change in the mass distribution that isn't perfectly symmetrical. Think less like a pulsating ball and more like a spinning dumbbell, or two objects orbiting each other. Physicists talk about a changing quadrupole moment.
Okay, spinning dumbbell, got it. So given that need for asymmetry and huge masses, what are the prime suspects? The cosmic generator.
Top of the list are binary systems. Two objects orbiting each other.
Like the Hulse-Taylor pulsar we talked about?
Exactly. Or pairs of white dwarfs, neutron stars, or black holes. Now remember, the Earth and Sun radiate waves, but it's minuscule.
Right, negligible.
But get two compact objects like neutron stars or black holes orbiting really close and fast, they become powerful sources. Neutron star binaries can spiral in and merge in maybe just 36 hours once they get close enough. Then specifically, black hole binaries merging, like GW150918. The strongest burst of waves comes right at the very end, during the merger itself.
Makes sense, maximum violence then.
Then there are supernovae, star explosions. Unless the explosion is perfectly symmetrical, which is unlikely, the asymmetrical movement of huge amounts of mass will generate gravitational waves.
Okay.
And maybe surprisingly, even a single spinning neutron star can emit waves, but only if it's not perfectly spherical. If it has slight deformities like lumps or mountains, even ones maybe only 10 centimeters high, that asymmetry as it spins will radiate gravitational waves, though likely very weak ones.
10-centimeter mountains on a neutron star. That's wild. Such a range of sources.
It is.
This then brings up a really big question, especially thinking about the very beginning of everything. What about primordial gravitational waves? Could waves have been generated right after the Big Bang?
Ah, yes.
Yeah.
That's a huge area of research and hope in cosmology. The idea is that during cosmic inflation, this hypothesized period of incredibly rapid expansion just fractions of a second after the Big Bang. Quantum fluctuations could have been stretched to cosmic scales, generating a background of gravitational waves that would still be permeating the universe today.
And how would we detect those?
The main hope is to look for their imprint on the cosmic microwave background radiation, the CMB, the afterglow of the Big Bang.
Okay.
Specifically, these primordial waves are predicted to leave a faint, characteristic swirling pattern in the polarization of the CMB light, something called B-mode polarization.
Has anyone seen that?
Well, there was huge excitement back in 2014. The BIC-EP2 collaboration announced they had detected this B-mode signal.
Wow. So case closed.
Not quite. Unfortunately, further analysis, including data from the Planck satellite, showed that the signal they saw could be entirely explained by dust within our own Milky Way galaxy.
Oh, so it was retracted.
Yes, the claim was retracted in 2015. It was a tough lesson, showing just how incredibly careful you have to be and how faint these potential signals are. But the search definitely continues with more sensitive experiments. Finding primordial gravitational waves would be revolutionary for understanding the birth of the universe.
Absolutely. Okay, so we know where they might come from. How do we actually listen for these cosmic whispers now, especially given how tiny that effect is, the whole width of a hair to the nearest star thing?
Right. The workhorses, the most sensitive detectors we have on the ground right now, are these incredible machines called laser interferometers. LIGO is the prime example.
How do they work, in simple terms?
Okay, the basic idea is you have two long arms, usually several kilometers long, set up at a right angle, like an L shape.
Like Lego's 4-kilometer arms.
Exactly. You shoot a laser beam, split it, send it down both arms, bounce it off mirrors at the ends, and bring it back together.
Okay.
Normally, the light waves from both arms should recombine in a specific way. But if a gravitational wave passes through...
it stretches one arm and squeezes the other.
Precisely. Just by that minuscule amount we talked about. This tiny change in arm length means the light travel times are slightly different, and when the beams recombine, the pattern changes. That's the signal we look for.
That sounds unbelievably sensitive.
It is. LIGO can detect changes in distance as small as 10 to the minus 18 meters. That's a tiny fraction of a proton's width. And ongoing upgrades are making them even more sensitive, increasing the volume of space they can listen to by maybe a factor of 1,000.
And it's not just LIGO, right? There's a network now.
Yes, a global network is crucial. We have Virgo in Italy, Kirash in Japan is coming online, and there are plans for even more sensitive future detectors like the Einstein telescope in Europe and Cosmic Explorer in the US. Having multiple detectors helps pinpoint sources and confirm signals.
It's still hard to grasp that level of precision. What are the main things fighting against you? What makes it so hard to get a clear signal?
Oh, the noise is the killer. Remember that strain is maybe 1021? That signal is incredibly faint, easily buried in noise.
What kind of noise?
There are several main types. There's shot noise, which is basically quantum randomness in the laser light itself, photons arriving slightly randomly.
Okay.
There's thermal noise, just random jiggling of atoms in the mirrors and their suspensions due to heat. Brownian motion, essentially.
Right, things vibrating because they're warm.
Exactly. And then there's seismic noise vibrations from the Earth itself. Earthquakes far away, trucks driving down the road nearby, waves crashing on the coast. All of it shakes the ground and the detectors. Isolating the mirrors from all that is a massive engineering challenge.
It really sounds like trying to hear a pin drop during an earthquake next to a rock concert.
That's not a bad analogy, actually.
It's such a huge data analysis problem, too. I understand there's even a project where people donate their home computer time.
That's right. Einstein at Home. It's a distributed computing project. Volunteers run software that analyzes data from LIGO and the GEO 600 detector, specifically looking for the very faint continuous signals we expect from those slightly deformed spinning neutron stars we mentioned earlier.
Using the power of the crowd to sift through the noise? Clever.
It taps into massive computational power that would be hard to get otherwise.
So ground-based detectors are amazing, but face these noise challenges. Are there plans to go to space?
Yes, absolutely. That's the idea behind LISA, the Laser Interferometer Space Antenna. It's a major project led by the European Space Agency with NASA involvement.
How would LISA work? How is it different?
LISA will be completely different in scale. Instead of kilometer-long arms on Earth, it will consist of 3 spacecraft orbiting the sun, forming a giant equilateral triangle.
How giant?
The arms, the distance between the spacecraft will be 2.5 million kilometers long.
Whoa, okay, that's big.
Yeah, and being in space gives it huge advantages. It's away from Earth's seismic noise, and you get a much, much better vacuum than we can achieve on Earth.
So it can hear different things.
Exactly. Its huge size and quiet environment will make it sensitive to much lower frequency gravitational waves than ground-based detectors can pick up.
Hmm.
Things like mergers of supermassive black holes at the centers of galaxies, or binary systems of white dwarfs in our own galaxy.
Very cool. So ground-based for high frequencies, space-based for low frequencies. But I understand there's yet another way people are trying to detect these waves using pulsars.
That's right, a completely different technique called pulsar timing arrays, or PTAs.
Okay, explain PTAs. They use pulsars as clocks.
Precisely. They focus on millisecond pulsars.
Hmm.
These are incredibly dense, rapidly spinning neutron stars rotating hundreds of times per second. And they emit beams of radio waves like lighthouses.
Uh-huh.
From our perspective on Earth, as these beams sweep past, we see incredibly regular pulses of radio waves. They're fantastically stable clocks. Some are more precise than the best atomic clocks we have on Earth.
Cosmic clocks. Okay, so how do gravitational waves fit in?
Well, if we connect this to the bigger picture, imagine a very long wavelength gravitational wave, maybe taking years or decades to pass through our part of the galaxy.
Okay, a really slow ripple.
As that wave passes between us and one of these distant pulsars, it slightly stretches and squeezes the space-time along the path. This changes the travel time of the radio pulses very slightly.
So the ticks from the pulsar clock arrive a tiny bit early or late.
Exactly. PTAs monitor dozens of these millisecond pulsars scattered across the sky, looking for these tiny deviations in the pulse arrival times.
But how do they know it's a gravitational wave causing it and not something else?
That's the clever part. A gravitational wave passing through should affect the timing of all the pulsars, but in a very specific, correlated way, depending on their position on the sky relative to each other.
A pattern.
Yes, a very distinctive quadrupolar pattern. Pairs of pulsars in certain directions should show correlated timing shifts, while pairs in other directions should show anti-correlated shifts. It's called the Hellingsdowns curve. Finding that specific pattern is the smoking gun for a gravitational wave background. And also found it. This is the really exciting news from just recently, June 2023. Several PTA collaborations around the world, including Niagara in North America, released their analysis of 15 years or more of data.
Odd.
They found the first strong evidence for this distinctive Hellingsdowns curve correlation. It's the first compelling evidence for a stochastic gravitational wave background.
Stochastic meaning, like a background hum.
Exactly. Not a single big event like a black hole merger, but a persistent, universe-filling hum made up of overlapping waves from countless sources.
Wow. What's making the hum?
The most likely source is the combined chorus of hundreds of thousands, maybe millions, of supermassive black hole binaries merging all across the universe throughout cosmic history.
So we're hearing the biggest black holes in the cosmos pairing up and dancing towards merger, averaged out over billions of years.
That's the interpretation. It's not just noise. It's like an acoustic map of galaxy evolution and these giant black hole interactions over cosmic time. A totally new way to study how galaxies and their central monsters grow.
That is absolutely mind-bending, hearing the universe hum with merging giants. Okay, shifting gears a bit. Could humans ever, make gravitational waves here on Earth? In a lab? I mean, everything we've talked about involves stars and black holes.
That's a fascinating, very speculative question. Theoretically, maybe. People have discussed concepts for microscopic sources. There's even this idea of a gas or gravity amplification by stimulated emission of radiation.
Like a laser, but for gravity.
Kind of. The proposal involved using things like Cooper pairs and superconductors. But we're talking way out on the frontiers of theoretical physics here. Generating detectable waves in a lab would require manipulating mass energy on scales far beyond anything we can currently conceive of, let alone achieve.
So probably not anytime soon.
Probably not. It pushes right up against the limits of our understanding, especially where gravity meets the quantum world.
Which leads perfectly to that ultimate frontier, doesn't it? Quantum gravity, and this idea of the graviton. What exactly is a graviton supposed to be?
Well, in our current understanding of particle physics, the fundamental forces, electromagnetism, the weak and strong nuclear forces, are all mediated by force-carrying particles, like the photon carries the electromagnetic force.
Right.
Quantum gravity theories predict that gravity should also have a force carrier, a hypothetical particle called the graviton.
What would it be like?
It's theorized to be massless, like the photon, but to have a property called spin 2, whereas the photon has spin 1. But the key word is hypothetical.
It hasn't been proven to exist.
Not even close. We don't yet have a complete successful theory of quantum gravity that fully describes the graviton and how it would work. It's one of the biggest unsolved problems in fundamental physics, unifying gravity, Einstein's world, with quantum mechanics, the world of particles.
And that's where it gets really tantalizing, right? Because if we did somehow discover a massless spin-2 particle,
That would almost certainly be the graviton.
and what would that mean?
Oh, it would be profound, absolutely revolutionary. It would be the first direct experimental evidence confirming that gravity can be quantized, finally uniting quantum theory with general relativity. It would reshape our understanding of reality at its deepest level, one of the biggest holy grails in physics.
Wow.
Yeah.
Okay. What an incredible journey we've taken today, seriously. From Einstein puzzling over these ripples in space-time,
His own doubts included.
right, to the decades of searching, the indirect proof from pulsars, and then finally LIGO hearing those black holes collide.
And now the PTA's hearing the cosmic hum.
It's just opened up this completely new way of observing the universe, hasn't it?
It really has. And its power, particularly for looking back towards the beginning, is immense.
Because the waves just travel straight through everything.
Exactly. They experience very little absorption or scattering, even over billions of light years. Unlike light or radio waves, which get blocked or altered by gas and dust.
So they can carry information from eras we could never see before.
Potentially, yes. Phases of the universe that were completely opaque to light might be transparent to gravitational waves. They could let us probe closer to the Big Bang than ever before.
It really makes you wonder, doesn't it? What other profound secrets are these cosmic ripples carrying? Secrets about the most violent events, maybe secrets about the universe's very beginning, just waiting for us to get better at listening.
There's so much potential still untapped.
Absolutely. Well, definitely keep those curiosity engines running. Okay, picture this. You're standing before this, just immense force of nature, something so powerful, it's literally carving the land around it, grinding away rock.
Oh, that's incredible.
And the water, over 168,000 cubic meters a minute at peak times, plunging down. And it's got this amazing green color because of all the ground up rock in it.
Rock flower, yeah. It's really something else.
That's Niagara Falls. And today we're doing a real deep dive into this icon that sits right on the U.S.-Canada border.
It's such a fascinating place, so much more than just the view.
Absolutely. We've dug into a whole bunch of sources. You shared historical stuff, geology reports, cultural takes, you name it.
A really comprehensive look.
Right. Our mission here is to get past that postcard image, uncover the hidden stories, how it formed, the challenges now, what keeps drawing people in.
There are definitely some surprising facts, some real aha moments in there.
Totally. Get ready to discover some things you probably didn't know about one of North America's most famous spots.
So where should we start? The falls themselves.
Yeah, let's start with the basics. When we say Niagara Falls, what are we actually looking at? Is it just one giant waterfall?
Good question. No, it's actually a group of three.
Three.
Yeah. You've got the really big one, Horseshoe Falls, that's mostly in Canada.
Right, the iconic curved one.
Exactly. Then, over in the U.S., you have the American Falls and the smaller Bridal Veil Falls. They're separated by islands, like Goat Island and Luna Island.
And the scale is just hard to grasp. How big are we talking, especially Horseshoe Falls?
It's massive. Horseshoe Falls is about 57 meters high, so what's that, 187 feet.
Wow.
And it's wide, really wide. About 790 meters, or nearly 2,600 feet across.
Okay, that's huge. And American Falls.
A bit shorter, maybe 21 to 30 meters high, depending on the rocks at the bottom, but still over 300 meters wide. The whole span, all three falls together, is over 1 kilometer wide.
That's an unbelievable amount of water. But you mentioned peak hours?
Yeah.
Does the flow change?
Oh yeah, definitely. The flow rate is actually managed. Horseshoe Falls has the highest flow rate of any waterfall in North America, over 50 meters tall, making it incredibly powerful.
That figure of 168,000 cubic meters a minute.
That's during peak tourist times. But the flow depends on Lake Erie's water level.
Yeah.
And, crucially, it's regulated by the 1950 Niagara Treaty.
A treaty, so humans are actively controlling it.
Absolutely. There's an International Niagara Board of Control. They divert a significant amount of water, especially at night and during the winter, the low tourist season,
Right.
for hydroelectric power. The flow can be cut roughly in half, down to about 1,400 cubic meters per second for the power plants.
Fascinating, balancing the spectacle with energy needs. Which brings us back to that color, that vibrant green. You said rock flower.
Exactly. It's not pollution or algae. It's the falls doing their work. The sheer force erodes the riverbed, grinding rock into superfine particles, rock flour.
And that stays suspended in the water.
Yep. An estimated 60 tons of dissolved salts and this rock flour go over every minute. It's what gives the water that distinctive, almost emerald green color. The falls are literally grinding themselves down and coloring the water.
That is such a wild detail. The falls are painting themselves. And it's not just rock and water, right? There's wildlife, too. You mentioned gulls.
Oh, yeah. It's a major bird area, especially for gulls in winter. Bonapartes, ring-billed, herring gulls. Something like 100,000 of them winter there.
Why so many?
It's on their migratory routes, there's good foraging, and importantly, the river below the falls doesn't usually freeze solid. So it's reliable open water for them. You can see tens of thousands on any given day in early winter.
Okay, that paints a really vivid picture of the falls today. But let's rewind. How did this massive thing even form? We're talking geology now, right?
Yeah, deep time geology. It all goes back to the end of the last ice age, the Wisconsin glaciation, around 10,000 years ago.
So melting glaciers.
Exactly. As these huge ice sheets retreated, the meltwater created the Great Lakes. The Niagara River formed as the main drain for the upper Great Lakes, carving a path through the landscape.
And it carved through something specific, the Niagara escarpment.
Right. The escarpment is basically a long cliff, a ridge. The river had to cut down through it.
And the way it cut through wasn't even which created the falls themselves.
Precisely.
Yeah.
That's the key to the falls formation and shape. Think of it like layers of a cake, but geological layers.
Okay, geological cake. I like it.
You've got a really hard, erosion-resistant layer on top of the Lockport Formation. That's the cap rock.
The tough layer.
Right. Underneath that, you have softer stuff, mainly shale, the Rochester Formation. And below that, even softer shales and sandstones in the Queenston Formation.
So the water wears away the soft layers faster?
Exactly. The river erodes the softer shale layers underneath, creating an undercut. Eventually, the hard cap rock layer above has no support, and huge sections just break off and collapse.
Ah, okay. And that process keeps repeating.
Constantly. That's why the falls have moved, retreated over time. It's this uneven erosion that created the falls and keeps shaping them.
How far has it retreated? It sounds like it must be a lot.
It is. Over the last, say, 11,000 years, the falls have moved about 10.9 kilometers. That's nearly 7 miles southward from where they first formed, near modern-day Queenston and Lewiston.
7 miles? That's mind-blowing. And the shape has changed, too.
Yep. Horseshoe Falls used to be more of a small arch, then it broadened into that horseshoe shape, and now, arguably, it's becoming more V-shaped due to the way the erosion is focused.
So if it keeps retreating, what's the long-term future? Will Niagara Falls disappear?
Well, the erosion rate is slower now, partly due to water diversion for hydro and some engineering. It's about 30 centimeters, roughly a foot, per year now. Historically, it was closer to a meter per year.
Still, a foot a year adds up.
It does. At the current rate, projections suggest it will take about 50,000 years for the falls to erode the remaining 32 kilometers back to Lake Erie. And then, essentially, the falls, as this dramatic drop, would cease to exist. It would become more like rapids, the river gradient evening out.
50,000 years. Okay, so we've got some time, but it's a powerful reminder of geological time and change.
Absolutely. And also how human intervention is now part of that geological story.
That's a perfect transition. Let's talk about that human element, especially the efforts to preserve this place. It wasn't always protected, was it?
No, definitely not. By the 1870s, things were getting pretty bad. Access was often controlled by businesses who charged fees. Goat Island was threatened by commercial development. Industry was encroaching. It was becoming kind of a tourist trap, losing its natural beauty.
So people started pushing back.
Yes, thankfully. A conservation movement, the Free Niagara movement, really took hold in the U.S. You had prominent figures like the painter Frederick Edwin Church, the famous landscape architect Frederick Law Olmsted.
Olmsted, who designed Central Park.
The very same. And architect Henry Hobson Richardson. They saw what was happening and were appalled. Olmsted, especially, visited Goat Island and was deeply affected. Church even reached out to Canada's Governor General to suggest an international park.
And Olmsted and James Gardner wrote a really important report.
They did. In 1879, their special report on the preservation of Niagara Falls was a game changer. It basically called for the state to buy the land around the falls, restore it, and make it public. They framed it as a sacred obligation to mankind. Powerful stuff.
A sacred obligation. Wow. Did it work?
It did. It led directly to the creation of the Niagara Reservation in New York in 1885. Governor David Hill signed it into law, making it New York's first state park.
The first state park in New York. That's significant.
And amazingly, Ontario created Queen Victoria Niagara Falls Park on the Canadian side that same year. A really remarkable parallel effort.
That cross-border cooperation is fantastic. And Olmsted had a vision for how the park should be managed.
Yes. He and Calvert Vaux followed up in 1887. Their idea wasn't to add a bunch of man-made attractions, but to restore and conserve the natural surroundings,
Right.
rather than to attempt to add anything there too. Balancing access with preservation was key.
That philosophy seems crucial. And efforts continued into the 20th century, like regulating water diversion.
Yes, the 1906 Burton Act and a 1909 treaty started limiting water diversion specifically to preserve the fall's appearance.
And then came that incredible event in 1969. They actually turned off American Falls.
It sounds unbelievable, right? But yeah, for several months in 1969, they built a temporary dam, a cofferdam, diverting the entire flow of the Niagara River over Horseshoe Falls.
Why on earth would they do that?
The U.S. Army Corps of Engineers wanted to study the rock face of American Falls, see if they could stabilize it, maybe remove the pile of fallen rock, the talus, at the bottom, that had built up after a big rockfall in 1954.
So they just dewatered it. What did they find? Anything surprising?
Well, tragically, they found the bodies of two people, a man who jumped and a woman. On the engineering side, they decided removing the talus would be too expensive and perhaps aesthetically undesirable. They did install bolts and sensors to monitor stability.
And then they just turned it back on.
Pretty much. In November 1969, they dynamited the temporary dam, and the water rushed back over American Falls. It must have been an incredible sight. For years after, Luna Island between American and Bridal Veil Falls was closed due to stability concerns.
Just amazing. What about modern preservation challenges? Are there new issues today?
There's always discussion. On the Canadian side, some debate the visual impact of tall hotel and casino developments near the falls. There was even a study suggesting they might increase mist, though that's debated.
And the U.S. side?
Ongoing efforts focus on restoration and enhancing the experience while preserving nature, like recent work on Three Sisters Islanders and upgrades at Prospect Point. It's a continuous balancing act.
Okay, that gives us a good sense of the physical falls and the efforts to protect them. Let's switch gears a bit and dive into the human history, starting with the name itself, Niagara. Where does that word come from?
It's actually a bit of a mystery, with several plausible theories.
Oh, like what?
One popular one is from an Iroquoian word, possibly Angera, meaning thundering water. Makes sense, right?
Yeah, that definitely fits.
Another theory connects it to a local First Nations group, the Neutral Confederacy, who are called the Niagara on some early French maps.
Okay. Any others?
Some suggest Anguiara, meaning point of land cut in two, or maybe Janiaco, noisy point or portage. The Mohawk word Anyara means the neck, referring to the strip of land between Lake Erie and Lake Ontario.
So lots of possibilities, all evocative.
And the modern Seneca name is Josco Sodo, which translates to the cliffs are standing, also very fitting.
It was clearly a significant place long before Europeans arrived. When did they first see it and report back?
Samuel de Champlain heard about it in 1604 from his party and described it based on their reports, but he didn't actually see it himself.
So who gets the credit for the first description?
Usually, Father Louis Hennepin, a Belgian missionary in 1677. He wrote about it after his visit, though it's possible some Jesuit missionaries saw it even earlier.
And the first scientific look. First painting.
The first scientific description came from Per Kalm, a Finnish-Swedish naturalist in the early 1700s. And the first known eyewitness painting was by Captain Thomas Davies, a British Army officer, in 1762. That really started to bring the image to Europe.
And then came the tourists. It really blew up in the 19th century, didn't it? Became the honeymoon capital.
Absolutely. By the mid-1800s, tourism was the main industry there. Theodosia Burr Alston, Aaron Burr's daughter, and her husband were the first recorded honeymooners way back in 1801.
Wow, 1801.
Yeah, and even Napoleon's brother Jerome visited with his bride. It became the place to go.
We also heard about famous visitors. John Franklin called it the first in the world for grandeur. And Frederick Douglass had a really profound reaction.
Yes, Douglass visited in 1843 and wrote powerfully about it. He said, "When I came into its awful presence, the power of description failed me. An irresistible power closed my lips." It just stopped him in his tracks.
That really captures the awe. And it was also important for the Underground Railroad.
Hugely important. Being right on the Canadian border, It was a major crossing point for enslaved people seeking freedom. There were conflicts, dramatic escapes. The Niagara Falls Underground Railroad Heritage Center does a great job telling those stories today.
It even has a place in the history of photography.
It does. One of the earliest known photographs of the falls is a daguerreotype taken around 1840 by an Englishman named Hugh Lee Pattinson.
A daguerreotype. That's really early photography.
Exactly. And get this, the little silhouetted figure you can see in the photo. It's thought to be Pattinson himself, having to stand perfectly still for the long exposure time.
That's fantastic. Standing there while his camera captures history. Okay, we have to talk about the Iron Scow incident. 1918. Sounds dramatic.
Well, it was pure drama. August 6, 1918. This flat-bottomed barge, an iron scow, broke loose from his tugboat upriver with two men aboard, Gustav Lofberg and James Harris.
Oh no. Heading for the falls.
Yep, drifting towards the brink of Horseshoe Falls. They managed to open the dedumping doors and ground it on some shallow rocks, maybe only 600 meters from the edge.
So they were stranded, just above the falls.
Exactly, for over a day. The rescue was incredibly tense, involving the Coast Guard, the Niagara Parks Police, the fire department. They eventually shot a line out using a Lyle gun, and the legendary local riverman, William Redhill Sr., went out hand over hand on the line to untangle it, allowing the men to be brought back in a breeches buoy.
Wow. Redhill Sr., a true hero. And the scow.
Amazingly, the scow stayed stuck on those rocks for over 101 years. It became a fixture. It only shifted significantly during a heavy storm on Halloween 2019, moving about 50 meters downstream. It's still there, though, slowly deteriorating.
Incredible. A piece of history just stuck there. You also mentioned the shape of Horseshoe Falls changing due to human intervention.
Yeah, that's right. Before the 1950s, the northeastern end of Horseshoe Falls was actually in the U.S., near Terrapin Point on Goat Island.
Oh, really?
But landfilling in 1955 extended Terrapin Point, and then more work by the Army Corps in the early 80s filled in more area, effectively straightening that end of the crest line. About 120 meters of the falls was eliminated.
So that's why sources now say it's mostly or entirely in Canada.
Exactly. Human engineering literally reshaped the boundary.
Okay, one last historical question. Did the falls ever actually freeze solid? People talk about that.
The river below the falls often freezes,
Right.
and the falls themselves get massively iced up almost every winter, creating incredible ice formations. But a complete freeze-up, stopping the water flow entirely, that's only happened once on record.
Only once. When was that?
March 29, 1848. A massive ice jam upstream on Lake Erie blocked the river's source, and the flow over the falls stopped for up to 40 hours.
40 hours. What was that like?
Eerie silence. Mills stopped working, factories went quiet, people could actually walk out onto the dry riverbed. Then the jam broke, and the roar returned.
Unbelievable. And those historical ice bridges people used to walk on.
Yes, before modern bridges, thick ice would sometimes form across the river below the falls, sometimes incredibly thick, like 100 feet thick. People did walk, even set up shanties on it, but it was dangerous. Tragically, in 1912, an ice bridge broke up suddenly and 3 people died. They haven't formed that thick since the 1950s, probably due to the ice boom and power diversions.
Okay, from natural history to human history, and now to engineering marvels, the bridges. Crossing that gorge must have been a huge challenge.
Absolutely. Building over that deep, powerful gorge was a major feat. We saw a whole evolution of bridge technology right there.
What was the first one like?
The very first was a light suspension bridge opened in 1848, mainly for carriages. But it was quickly replaced in 1855 by a much more substantial one, the Niagara Falls Suspension Bridge.
And that one's famous.
Very famous. It was a double-decker, trains on top, carriages and pedestrians below, and crucially, it was used by Harriet Tubman and others on the Underground Railroad to help enslaved people escape to freedom in Canada, a really important historical link.
Wow, is that bridge still there?
No, that one was replaced in 1897 by the bridge we now call the Whirlpool Rapids Bridge.
Yeah.
It's a steel arch bridge, and it's actually the oldest bridge still spanning the Niagara River today.
Okay. And closer to the falls, there was the Honeymoon Bridge. Sounds romantic.
It was. Officially, the Upper Steel Arch Bridge opened in 1897. It was a very popular spot for tourists, but it had a dramatic end.
Oh, what happened?
In January 1938, a massive ice jam in the river pushed against the bridge's abutments with incredible force. The supports buckled, and the entire bridge collapsed onto the frozen river below. Huge spectacle.
Just collapsed. So what replaced it?
The Rainbow Bridge, which opened in 1941, it was built higher up to avoid ice issues. That's the main road bridge closest to the falls today, the one that offers those fantastic panoramic views.
It's incredible how engineers tackled that environment. And that same power, the river's energy, obviously drove industry too.
For centuries, people looked at that water and saw power. As early as 1750, Daniel Jonker built a small mill race, a canal, to power a sawmill. Just the beginning.
Who are the early pioneers of hydropower there?
Augustus and Peter Porter tried to expand the canal idea in 1805, but the first proper hydroelectric generating station came in 1881, built by Jacob Skolkoff. It produced direct current DC electricity.
But DC doesn't travel well. Right, AC was the key.
Exactly. The big breakthrough was in 1893 when Westinghouse Electric, with Nikola Tesla's AC patents, designed a large-scale alternating current system for Niagara Falls. It went live in 1895. That really kicked off the modern era of hydroelectricity.
And big names got involved in funding it.
Oh, yeah. J.P. Morgan, John Jacob Astor IV, the Vanderbilts,
Yeah.
they backed the construction of massive underground tunnels, conduits to feed generating stations. By 1896, they were producing serious power, sending it all the way to Buffalo.
And Canada followed suit.
Private companies did, yes. But then Ontario took a different path in 1906, establishing Ontario Hydro and moving towards public control of power generation and transmission.
Then there was a major setback in the 1950s, a landslide.
Yes, in 1956, a huge landslide destroyed a large part of the biggest power station on the U.S. side, the Skolkoff Station. It was a disaster.
How did they respond?
It led to the Niagara Redevelopment Act in 1957. This gave the New York Power Authority the green light to fully develop the U.S. share of the river's power potential, leading to the massive Robert Moses Niagara Power Plant.
And today, how much power are we talking about?
It's huge. The Robert Moses plant and the associated Lewiston pump generating plant have a combined capacity of 2.4 gigawatts. It's still New York State's largest electricity producer.
And they divert a lot of the river's flow.
Between 50 and 75%, depending on the time of day and year. The water goes through huge tunnels, bypassing the falls completely, spins the turbines, and then rejoins the river downstream.
You mentioned the Lewiston plant is a pump generating plant. How does that work?
It's pretty clever. During off-peak hours, when electricity demand is low and cheaper, they use power to pump water from the river up into a large reservoir.
Okay, storing potential energy.
Exactly. Then, during peak hours, when demand is high, they release that stored water back down through turbines, generating extra electricity when it's needed most. It's called pump storage.
Very efficient. And this is all still balanced with tourism, right? That treaty.
Yes, that 1950 treaty is crucial. It mandates that during daytime tourist hours, roughly April to October, enough water must go over the falls to maintain that unbroken curtain of water. So power generation is reduced during those times.
And the ice boom we mentioned, that helps power generation too.
Right. It's installed each winter. It's a string of floating pontoons that stretches across the river upstream. It helps prevent large chunks of ice from flowing downriver and potentially damaging the power plant intakes or causing ice jams near the falls.
And there was a major tunnel project recently too.
Yes, the Niagara Tunnel Project on the Canadian side finished in 2013. A massive new tunnel, over 10 kilometers long and 12 meters wide, to feed the Sir Adam Beck generating stations. It boosted their capacity significantly, enough to power about 160,000 more homes.
So constant engineering to harness that power. What about other impacts, like shipping?
Well, the falls are obviously impassable for ships. That's why the Welland Canal was built nearby, connecting Lake Erie and Lake Ontario and bypassing the falls entirely. It shifted shipping traffic away from Buffalo, but allowed industries powered by Niagara's electricity to thrive elsewhere in the region.
Though you mentioned some economic decline later.
Yeah, like many industrial areas, the region faced challenges from the 1970s onwards as heavy industry shifted. But the falls themselves, their name, it lives on Niagara University, airports, even an asteroid named Niagara. Its presence is huge.
Okay, now for maybe the most sensational part of the Niagara story. The daredevils, people actually going over the falls or walking across the gorge. It sounds insane.
It absolutely captures the imagination, doesn't it? The sheer audacity. And it started quite early, though maybe not with humans initially.
What do you mean?
Well, one of the first big spectacles back in 1827 involved sending an old ship, the schooner Michigan, over the falls. They loaded it with animals, buffalo, bears, geese, a dog, and effigies of people.
They sent animals over, seriously.
Seriously, it was a P.T. Barnum-style publicity stunt. Apparently, the bears jumped free before the plunge, and the geese flew off, but yeah, grim beginning.
Okay. Then came the human jumpers, into the gorge below.
Yeah. Sam Patch, who called himself the Yankee Leapster, famously jumped from a high platform into the gorge below the falls in 1829 and survived. He became a folk hero.
But not everyone was so lucky trying to conquer the rapids.
No. Captain Matthew Webb, the first man to swim the English Channel, tried to swim the Whirlpool Rapids below the falls in 1883 and drowned. The currents are incredibly dangerous.
But the ones who really became legends are the barrel riders, starting with Annie Edson Taylor.
Annie Edson Taylor, October 24th, 1901. A 63-year-old schoolteacher. She decided going over the falls in a barrel would bring her fame and fortune.
63 years old. Was she the first person to try it?
The first person known to go over and survive. And remember what we heard earlier?
Oh, right. She sent her cat over first.
Yep. Sent her cat, Ionia, over in the barrel for a test run a few days before. The cat survived. So Annie figured, okay, my turn.
Unbelievable. And she survived.
She did. Battered and bruised, with a cut on her head, but alive. Her first words were reportedly, "No one ought ever do that again."
Did people listen?
Not really. The allure was too strong. It's illegal now, of course, huge fines and potential jail time on both sides. But others tried. Charles Stevens died trying in 1920. His anvil, meant for ballast, tragically went through the bottom of his barrel.
Oh, horrific. Who else survived?
Bobby Leach went over in a steel barrel in 1911 and survived, but broke both kneecaps and his jaw. He needed rescuing by that same Red Hill senior who helped the Scowmen. Jean Lussier survived in a large rubber ball in 1928.
A rubber ball.
Okay.
And then there was that incredible survival story in 1960, the miracle at Niagara.
Just astonishing. A small boat lost power upriver with 3 people aboard. 17-year-old Dean Woodward was pulled from the river by bystanders just feet from the brink of American Falls.
Wow. Close call.
Her 7-year-old brother, Roger Woodward, went over Horseshoe Falls wearing only a life jacket.
A 7-year-old over the falls.
Yes. And incredibly, he survived the plunge. The crew of the Maid of the Mist spotted him in the turbulent water below and threw him a life ring. They rescued him. A true miracle. Their uncle, who was driving the boat, sadly did not survive.
That is unbelievable. Just defies logic. Have people tried it in more modern times?
Oh, yeah. Carol Selchek survived in a barrel in 1984, got fined, then tragically died the next year trying to recreate a similar stunt in Houston. Steve Trotter was the youngest survivor in 85 and did it again with a partner in 95.
Even teams tried it.
Peter DeBernardi and Jeffrey Petkovich went over together in a barrel in 1989. But there were more tragedies, too. Jesse Sharp tried it in a canoe in 1990, no helmet, no life vest. His body was never found. Robert Overacker tried on a jet ski in 1995 with a rocket-propelled parachute that failed. He plunged to his death.
So dangerous. And some people have survived going over unprotected, without a barrel or anything.
It sounds impossible, but yes. Kirk Jones famously survived an unprotected plunge over Horseshoe Falls in 2003, seemingly on purpose. He was fined and banned. He died attempting it again in 2017 in an inflatable ball. There have been a few other cases since 2003, usually suicides who unexpectedly survived the fall. It highlights how unpredictable survival is.
Just incredible stories. Now, what about the tightrope walkers? They weren't going over the falls, but across the gorge, right?
Correct. A crucial distinction. They walked on tight ropes, strung high above the Niagara Gorge, downstream from the falls, usually near where the Rainbow Bridge is now.
And the most famous was Blondin.
Jean-François Gravelet, known as the Great Blondin. He was the first to cross in 1859. He did it multiple times, adding crazy stunts blindfolded, pushing a wheelbarrow, carrying his manager on his back.
Carrying his manager.
On his back. He became a global sensation. The Prince of Wales even came to watch one of his crossings.
Amazing. Was he the only one? Was there a woman who did it?
Yes. Maria Spelterini, an Italian woman, crossed in 1876, the first and only woman to do it, and she added her own flair, crossing blindfolded, with her ankles and wrists manacled, even with peach baskets strapped to her feet.
Peach baskets on her feet. Incredible skill and nerve.
Absolutely. A real pioneer.
And then, much more recently, Nick Walinda brought high wire walking back to Niagara in a big way.
It was huge. In 2012, he was the first person to walk on a wire directly over the falls area in over a century. His walk was further upstream, near the brink of Horseshoe Falls, from the U.S. side to the Canadian side.
That must have required special permission.
Big time. Legislation had to be passed on both sides. It was a 550-meter walk, the longest unsupported tightrope walk in history at the time. And famously, he carried his passport and presented it to Canadian officials upon arrival.
A very symbolic act. What an image. Okay, from daredevils to the millions who visit just to look. Let's talk tourism and culture. It's a massive draw, right?
Huge. Peak season is summer, of course. The falls are floodlit every night, creating a really magical spectacle. Visitor numbers are staggering. Projections were heading towards 28 million annually over a decade ago. It's one of the world's top tourist destinations.
And the Maid of the Mist boat tour is probably the most famous attraction?
Definitely the oldest and best known. It's been operating in some form since 1846, taking people right into the misty basin of Horseshoe Falls. It's named after a mythical Native American figure, though that caused some controversy later. Yeah, in the 90s, some Native American groups objected to the recorded narration, telling what they considered a fabricated legend, and the company eventually stopped using it. Shows how interpretations change. The Canadian boats are now operated by Hornblower Cruises, but offer a similar experience.
What are the main things to see and do on the U.S. side?
Prospect Point Park is great, has the observation tower for views, and it's where you board the Maid of the Mist. Goat Island is a must, incredible views between the falls, and the Cave of the Winds experience takes you down elevators to walkways right near the base of Bridal Veil Falls. You get soaked.
Seems intense. What else?
There's the Three Sisters Islands, connected by bridges, very scenic. The Power Portal near the old school cuff site has a statue of Nikola Tesla. Helicopter tours give you an amazing aerial view. And there's the Seneca Niagara Casino and Hotel right there, too.
And on the Canadian side,
Right.
often said to have the more panoramic views.
Generally, yes, because you're looking across at both American and Horseshoe Falls. Queen Victoria Park is the main area. Beautifully landscaped gardens, great viewing platforms, and underground passages for the journey behind the falls experience.
Journey behind the falls.
Yeah, you go down in elevators and walk through tunnels that open up onto observation decks almost directly behind the sheet of water of Horseshoe Falls. Very loud, very misty, very cool.
What else stands out on the Canadian side?
The Skyline Tower offers the highest viewpoint. There's the Whirlpool Aero Car, a cable car that goes across the Niagara Whirlpool downstream. Lots of shops, restaurants, two big casinos, Fallsview Casino Resort and Casino Niagara. And the Niagara River Recreational Trail is great for walking or cycling along the gorge.
So, tons to do. But beyond tourism, Niagara Falls has seeped into popular culture, hasn't it? Movies, books, music.
Oh, absolutely. It's been a backdrop and a symbol for ages. That 1953 movie Niagara with Marilyn Monroe really put it on the map for a new generation, made it seem glamorous and dangerous.
Any other notable film appearances?
Superman Second had a key scene there. Parts of Pirates of the Caribbean at World's End were conceptually set there, linking it to the edge of the world. Even Woody Woodpecker had a cartoon called Niagara Fools. And the magician, David Copperfield, made the falls vanish in a TV special in 1990.
It's inspired writers, too.
Definitely. H.G. Wells used it strategically in The War in the Air. Numerous poets like Jose Maria Heredia from Cuba, Americans like John Neal and Lydia Sigourney were inspired by its power and beauty. Mark Twain even wrote a funny piece about Adam and Eve being disappointed by it compared to other wonders.
And music.
Composer Frédéric Groffet wrote a Niagara Falls suite in the 60s, commissioned for the opening of the big hydro project. Michael Dougherty wrote a concert band piece called Niagara Falls in the 90s. It definitely inspires soundscapes.
And finally, visual art. It seems like every landscape painter had to paint Niagara Falls.
Pretty much. One art historian called it the most popular and tritest single item of subject matter in 18th and 19th century American art, meaning it was painted almost too much.
Okay. So it was iconic, but maybe overdone.
But artists rushed there to use every new technology, engravings, lithographs, those early daguerreotypes like Pattinson's, even early movies. They all wanted to capture its unique power. Frederick Edwin Church's painting Niagara from 1857 is probably the most famous masterpiece capturing its scale and light. Thomas Cole, Albert Bierstadt, all the big names painted it.
Wow. So we've covered a lot of ground today. From the sheer geological force that's still shaping the land, to the human story, the preservation battles, the harnessing of power, the daredevils, the art. It's quite a tapestry.
It really is. You see this constant interplay between this immense natural power and human ingenuity, ambition, and sometimes maybe folly. It reflects so much about our relationship with the natural world.
It really does. Okay, as we wrap up this deep dive, here's something to think about. We know the falls are geologically temporary, constantly eroding, even with our interventions. They will eventually disappear.
Right, in that very long-term view.
So looking ahead, maybe not 50,000 years, but in our time and the near future, how do we continue to manage this relationship? How do we keep balancing the urge to use its power, enjoy its beauty, profit from it, with what that early report called the sacred obligation to preserve its wild, powerful essence for generations to come? It feels like a question that's always evolving, just like the falls themselves. Imagine a film. Okay, so Visionary, it basically creates the blueprint for future cities for robots. But then it's so controversial, it gets chopped up, lost for decades.
It's wild, isn't it? One of those films that changed everything that came after. Even though, for the longest time, hardly anyone could actually see the whole thing as it was intended.
Exactly. So today we're doing a deep dive into Metropolis. You know, the massive 1927 German silent science fiction film. We've got loads of material, historical accounts, film analysis, even production notes.
Yeah, and our mission really is to give you a kind of shortcut to understanding why Metropolis is still such a giant of cinema.
Yeah.
We'll unpack its artistry, which was totally revolutionary.
And the production, which sounds incredibly tough.
Oh, absolutely. And its message is complex, sometimes kind of contradictory, and of course, its influence, which is just everywhere. You should get ready for some aha moments because, well, there's a lot here.
Okay, let's jump right in. Where did this whole thing start? I mean, Metropolis was really pioneering, wasn't it? A feature-length sci-fi film.
Totally groundbreaking for its time.
Yeah.
Directed by Fritz, based on a novel by Thea von Harbo, who was married to him then, and she actually wrote the novel as a film treatment, which is interesting.
Right, planning ahead. And it was produced by Eric Palmer for UFA, the big German studio, during the Weimar Republic. That whole period between the wars has such a fascinating, kind of chaotic time for Germany, but amazing for art.
And the setting Lang created, this futuristic city, Metropolis. It's a dystopia, really. You've got the rich industrialists living way up high in these enormous skyscrapers.
Literally looking down on everyone else.
Yeah, exactly. And then you have the workers who live and toil underground, basically just keeping the city running. It's such a stark visual metaphor for class division.
So powerful. And the look of the city itself, where did that come from? I know Lang visited New York.
He did, yeah, in 1924. He famously said the film was born from seeing those skyscrapers. He called them a vertical sail, scintillating and very light.
A luxurious backdrop. Wow.
Suspended in the dark sky to dazzle, distract, and hypnotize. You can really feel that sense of awe and maybe a little bit of fear in the film's design. That verticality, the scale.
And that look fed into Art Deco, right? Or maybe helped shape it.
Oh, it definitely propelled Art Deco's popularity in Europe and America. But the film style isn't just Art Deco. It's more eclectic.
Mm.
You know, it blends that sleek functionalist modernism with these quite strong Gothic elements.
Gothic. Where do you see that?
Well, think about the catacombs beneath the city, the big cathedral, even Rotwang, the inventor's house. It's got this older, almost medieval feel mixed in with the futuristic stuff. It creates this really unique, layered world.
And there are other layers too, aren't there? Like biblical references.
Loads of them. Maria tells the workers the story of the Tower of Babel. It's a key scene, tying into the whole head and hands theme. And then Frater has that hallucination.
Where he sees the false Maria as the whore of Babylon from the Book of Revelation. Pretty heavy stuff for a silent film.
Absolutely. And beyond the Bible, the film is just soaked in the anxieties of the Weimar period. Industrialization, mass production, these were huge issues. Plus, ideas about American modernity and even hints of the rising political extremes, like fascism and communism. It's a real product of its time.
So you have this incredibly ambitious vision, drawing on all these sources. Actually making it must have been insane. The production is legendary for being difficult.
Oh, difficult is putting it mildly. It was epic, almost disastrously so. Think about modern blockbusters with huge budgets and long shoots. Metropolis kind of wrote the playbook.
How long did it take?
17 months, 310 days and 60 nights of filming between 1925 and 26. Just think about that stamina.
Unbelievable.
And the cost, astronomical. Over 5 million Reichsmarks, which today is something like 21 million euros. More than 3.5 times what they originally budgeted.
Wow, no wonder the producer, Palmer, got fired during the shoot.
Exactly, it was a massive gamble. And the conditions for the actors, well, they were pretty brutal too.
I've read about the flood scene. Brigitte Helm, who played both Maria and the robot.
Right, she and about 500 kids, poor kids from Berlin, had to spend 2 weeks in freezing water. Lang apparently insisted it be kept cold for authenticity.
That's harsh.
It really was. And Helm apparently fainted during the robot transformation scene because the costume was so rigid and tight. She got cuts and bruises from wearing it. It was made of this stuff called plastic wood.
Ouch. But then there's that other story from Thea von Harbo, the writer.
Yeah, it's a fascinating contrast. She said for those child extras who were apparently quite malnourished, the set was like a paradise. They got warm rooms, toys, playtime, hot meals 4 times a day.
So for them, it was maybe the best part of their lives at that moment, despite the cold water.
It seems like it. She said they were the most enthusiastic collaborators. It
Mm.
just shows you the extremes on a set like that, poverty meeting movie magic.
And speaking of magic, the special effects were groundbreaking. Eugenschiften.
Ah, yes, the Shifton process. Genius. Using mirrors, basically, to make it look like the actors were inside these huge, detailed miniature sets.
Such a clever trick. Hitchcock used it later, didn't
He
he?
did, yeah, in blackmail. It was a really influential technique.
Yeah.
And then, of course, there's the robot itself, the machine and mensch.
Instantly iconic. How did they actually build that?
The sculptor, Walter Schultz-Mittendorf, made it. They did a full plaster cast of Brigitte Helm's body.
Must have been uncomfortable.
You'd think so.
Oh.
And then built the robot costume around that cast using that plastic wood material.
Mm-hmm.
Once it hardened, it was totally rigid. Hence the cuts and bruises for Helm. A tough gig, physically and mentally, I imagine.
Okay, so we've got this incredible, difficult production creating this amazing world. Let's talk about the story itself, the plot. It revolves around a few key people.
Pretty much. You've got Joff Fredersen, who's the master of Metropolis, the big boss. Right. Then his son, Freder, who starts off kind of naive and privileged. There's Maria, who's this almost saintly figure for the workers.
And then there's Rotwang, the inventor. Bit of a mad scientist vibe.
Definitely. And Freder's journey is really the core. He's living the high life, totally unaware, until he sees Maria. That encounter sends him down into the machine rooms.
And he sees that horrific accident, right? The machine explosion.
Yeah, and he has this vision of the machine as Moloch, the biblical demon, devouring workers. It completely shakes him up and makes him realize what's actually happening in his father's city.
And the dynamic between his father, Fredersen, and Rotwang is key too, isn't it? There's some history there.
Oh yeah, a lot of history. Rotwang was in love with Hel Fredersen's wife, Freder's mother, before she died. He blames Fredersen.
Ah, okay, so Rotwang's got a grudge.
A massive one.
Yeah.
And he's built this robot, the Maschinenmensch, originally to sort of resurrect Hel. But Fredersen wants him to make it look like Maria instead, to manipulate the workers.
So while this is going on, the real Maria is kind of like a prophet to the workers.
Exactly. She's preaching peace and patience, telling them a mediator will come to bridge the gap between the head and the hands.
And Freder hears this and thinks, maybe that's me.
Pretty much. He's completely captivated by her message and, well, by her. But then Rotwang kidnaps the real Maria.
And unleashes the fake robot Maria.
Right. And this robot Maria is the total opposite. She incites riots, tells the workers to destroy the machines.
Mm-hmm.
Rotwang's plan is basically chaos, ultimately aiming to destroy Fredersen, Freder, the whole city.
And the workers actually listen to the robot Maria.
They do. They smash the heart machine, which leads to the underground workers' city flooding. It's total disaster, and their own children are trapped.
Oh my God. So how does it resolve? It sounds like everything's falling apart.
Well, the real Maria escapes, and she and Freder race to save the children from the flood. It's incredibly dramatic. Meanwhile, the workers capture the false Maria and burn her at the stake.
And they see she's a robot.
Yep, the metal shows through the flames.
Yeah.
Then Rotwang, who's gone completely mad by this point, thinks the real Maria is his lost love Hel, chases her onto the cathedral roof.
Then Freder fights him.
Yeah, there's a struggle, and Rotwang falls to his death.
Phew. Intense. And it all leads to that final famous image.
Exactly, that final inner title. The mediator between the head and the hands must be the heart. And you see Freder physically take his father's hand, the head and Grot's hand, the foreman representing the workers, the hand.
And brings them together, the heart connecting them.
Precisely. It's a very direct, very visual representation of the film's core message about needing empathy and understanding to bridge that huge class divide.
Such a powerful ending. But despite all this vision and drama, the film didn't exactly get rave reviews initially, did it?
No, not at all. It was really mixed. Critics at the time could see it was visually stunning, powerful images, amazing special effects.
Yeah.
We've talked about how advanced they were.
But they didn't like the story.
Generally, no. Words like naive, trite, ludicrously simplistic were thrown around regarding the plot and its politics.
Didn't H.G. Wells hate it?
He did. Famously called it quite the silliest film, which, looking back, seems incredible. But it shows how maybe out of step it was with contemporary expectations.
And it was long, right? The original cut.
Super long for the time. About 153 minutes. That length was a big problem for distributors. So pretty soon after the German premiere, it got drastically cut.
How much was cut?
A lot. Different versions were released internationally, often much shorter, and key plot points just vanished. Like the whole backstory with Hel, Rotwang's motivation, gone in many versions. Nearly a quarter of the film was lost.
Wow. And even Lang himself later seemed a bit down on the film.
Yeah, he did express dissatisfaction, called it silly and stupid later in life, which is complicated. Part of it might have been the Nazi Party's weird fascination with it.
Goebbels liked it.
Apparently, yes. He was impressed by its message and supposedly wanted Lang to make films for the Nazis, which Lang definitely did not want to do.
Okay.
And then there was his divorce from Thea von Harbu, who did join the Nazi Party. So, yeah, complex feelings there.
A really tangled legacy. But that led to this whole other story, the decades-long quest to actually restore the film.
Exactly. Because so much was missing for so long, people spent decades trying to piece it back together. It became this kind of cinematic holy grail.
What were the big milestones in getting it back? I remember the Giorgio Moroder version in the 80s.
Right, 1984. That was really the first serious attempt at restoration. People had mixed feelings about the soundtrack he added with, Freddie Mercury, Bonnie Tyler, very 80s pop.
Yeah, definitely a choice.
But Moroder himself said something interesting. I didn't touch the original because there is no original, which really shows you how fragmented the film was then. His version, controversial soundtrack aside, brought a lot of attention back to Metropolis.
Okay, so after Moroder.
Well, a huge step was the 2001 Restored Authorized Edition. They found more bits of lost footage from archives around the world and integrated them. That version was actually the first film ever put on UNESCO's Memory of the World Register.
Recognizing it as like a crucial piece of world heritage.
Precisely. But the real game changer came later.
The discovery in Argentina.
Exactly. In 2008, they found a 16-millimeter negative copy in a museum archive in Buenos Aires. Just incredible luck. It contained about 25 minutes of footage nobody had seen in decades.
Wow. Like finding buried treasure.
Totally. And then a few more scenes turned up from New Zealand. And the key to putting it all back together was the composer Gottfried Huppertz's original score. His handwritten notes basically acted like a map.
Showing where the missing pieces should go.
Yeah. It allowed them to reconstruct the film sequence by sequence, getting it incredibly close within about 5 minutes of Lang's original 153-minute runtime. That became the 2010 complete Metropolis restoration.
That's an amazing story in itself, the dedication to bring it back.
It really is.
Yeah.
And it paid off. Now, Metropolis is pretty much universally seen as, one of the greatest and most influential films ever made, no question.
And the influence is just undeniable, isn't it? You see it everywhere.
Absolutely. In film, the most obvious example is probably C-3PO in Star Wars. George Lucas has been open about the Maschinenmensch being a direct inspiration.
Right, you can totally see it. And in music.
So much music. Queen's Radio Gaga video is maybe the most famous. They used actual film clips and even inserted the band into scenes.
Yeah, that's iconic.
And David Bowie's whole Diamond Dogs era.
Yeah.
Motorhead had a song called Metropolis, Janelle Monáe's concept albums, and her whole android persona.
Oh, yeah, Cindy Mayweather.
Exactly.
Yeah.
Even Beyoncé has rocked Maschinenmensch-inspired outfits. It just keeps echoing.
And outside music and film.
Well, there's a Metropolis manga and anime adaptation from the early 2000s. It pops up in graphic novels like The League of Extraordinary Gentlemen, video games, even referenced on shows like RuPaul's Drag Race.
Yeah.
It's truly permeated the culture.
So all that restoration work, finding those lost reels, it really cemented its place, didn't it?
Yeah.
Allowed us to see the full picture, or near enough.
Definitely. It went from being this fragmented, almost mythical thing to a tangible masterpiece you can actually watch and appreciate in something close to its original form.
So wrapping up then, we've seen how Metropolis, born from Lang's awe at New York and skewed in those Weimar-era anxieties, it started as visually stunning, but maybe narratively shaky for critics back then.
And evolved into this undisputed classic. Its journey through being cut apart and then painstakingly restored is almost as dramatic as the film itself, a real testament to its power.
And its influence just keeps going. Across a century of art, music, design.
Yeah.
It's remarkable.
It really is. So thinking about that core message again, the struggle between the head, the intellect, the bosses, and the hands, the labor, the workers, and the idea that the heart, empathy, connection is the mediator.
Yeah.
Well, what does that say to us now, with all the complex tech shifts we're facing today? Things like AI, automation. They're creating new kinds of divides, maybe. Could that message about the heart still apply? How do we mediate those gaps? It's just something to think about, maybe.